A very long wire carrying a current I is bent into this shape. It's very long and straight over here. It's curved into 3/4 of a circle starting there. And it's bent again right here into another long and straight segment. Find the magnetic field produced by this entire current at the center of the 3/4 circle. This current may look complicated, but things will look a lot simpler when we divide it into segments. Let's divide it into 3 segments: 1, 2, and 3. Segment 1 is a straight current, and we want to find its magnetic field along this straight current. We can use Biot-Savart Law for this one. So dB is mu naught over 4 pi times IdL cross the unit vector r divided by r squared. For segment number 1, the dl goes in the direction of I, so dl goes to the right. R goes from the source to the point we're interested in. This is the source. The point we're interested in is over there, so R goes to the left. The angle between those two vectors is 180 degrees. Since sine 180 degrees is 0, this dB is 0. And this is true for every segment of the IDL. So the entire segment gives us a magnetic field of 0. The field produced by a straight current along that straight current is 0. Segment 2 is a circular current, and we want to find its magnetic field at its center. We will again use Biot-Savart Law. Let's look at this IDL, the point current source. The dl goes in the same direction as the current, that way, and the r goes from the source to the location we are interested in, so r goes that way. So the dl and the r are perpendicular to each other, and that is true for every segment of the dl. So the sine, the angle between these two, is sine 90 degrees, which is 1. So this equals to mu naught over 4 pi times I times dl times the length of the unit vector, which is 1, times sine 90 degrees, which is also 1. So it's just IdL on the top, and then r squared. And this r here is the big R. So it's big R squared down here. dB is a vector, so it has a direction. If I use my thumb to follow the current, at the center of the circle, the magnetic field, my curved forefingers are coming out of the paper, so the field at the center, the dB, is out of the page. To find the magnetic field produced by this entire segment 2, right over here, we would have to integrate the dB, the vector. But because every dB has the same direction, that means to find the magnetic field produced by the second segment, we can just integrate the magnitude of dB. So this is the integral of that, mu naught over 4 pi IdL over r squared. Anything that's a constant can be taken out, so we can take out mu naught I over, and 4 pi is also a constant. Big R is a constant. What's left would be the integral of dl. So this is mu naught I over 4 pi r squared. And what is the integral of dl? dl is little segments of the current along this 3/4 of a circle. So the integral of scalar dl is the length of this entire segment, which is 3/4 of the circumference. So it is 3/4 times 2 pi r. And when we simplify this, we'll get 3/8 mu naught I over R. And it's the out of the page direction. For segment 3, we have a very long straight current, and we want to find the field produced by that long straight current a distance r from that current. Now, we know that we can use Amperes law to find the magnetic field produced by a long straight current, but that long straight current would have to go very long on this side and continue on and very long on that side. So this is only half of a very long current. And in order for us to use Amperes law, the closed integral of B dot dl equals to mu naught times the enclosed current, to find that magnetic field produced by this segment of the current, we will first have to pretend that we have a long straight current. So we have to pretend first that this current goes on and on to the left. So let's look at this very long straight current. We want to find the magnetic field over here a distance r away, so first we have to make an Amperian loop. To use symmetry, our Amperian loop will be a circle. Our circular Amperian loop will look like this, going around this long straight current. The Amperian loop has to go through the location we are interested in, so the Amperian loop would have a radius big R. And we are going to make our Amperian loop in the same direction as the magnetic field produced by this segment 3. So if I use my thumb to follow the current, the fingers will go up in the front and down in the back. So the Amperian loop would go up in the front and down in the back. With the symmetry, we would have this integral B dot dl equals to, we'll be able to take the B out of the integral, because by symmetry, the magnetic field's strength will be the same everywhere on that Amperian loop. The cosine, since we chose the B and the dl to be in the same direction, this will be cosine 0 degrees. We can also take it out of the integral. What's left in the integral would be the integral of dl. So this will give us B times 1 times the integral of dl. Now this dl is the imaginary Amperian loop. It's this green circle right here. Since the radius is r, the big R, the integral of dl would be the length of the Amperian loop, 2 pi big R. And on this side, we know this integral should equal to mu naught times the enclosed current. The current inside this Amperian loop is I. So it's mu naught times I. Therefore, I can divide by 2 pi r on both sides, and we'll find the B to be mu naught I over 2 pi r. But of course, this magnetic field is the field produced by this entire long straight current. But our real current is only half as long, so the magnetic field produced by segment 3 is this divided by 2. Which means it's mu naught I over 4 pi r. If I use my thumb to follow the current in segment 3, my curved forefingers will come out of the paper. So this B3 is out of the paper. Now we can find the net magnetic field over there produced by this entire current. All we have to do is to use the superposition principle and add the magnetic field produced by each segment together by adding vectors. Of course, right now B1 is 0, and B2 and B3, they are in the same direction, so we can just add their magnitudes together, and this is what we get. And its direction is out of the page. While we are at it, I want to point out that there is a dl in the Biot-Savart law. There is a dl in Amperes law as well. But those two are very different dl's. In the Biot-Savart law, The IDL is a point current source, so the DL is a segment of the current, while the DL in Amperes law is the imaginary Amperian loop. For example, for segment number 3, when we were looking at this very long straight current, the Amperian loop is an imaginary circle. There's no actual circle over there. The DL is an integral along this imaginary circle. It is not the same as this actual current. However, in Biot-Savart law, this DL is the actual current. This is not.